Reference counting. What is it? How does it work? And why not just use std shared pointer? That is what we're talking about today. It's probably the #1 question that people have when they see Hazel's code base. What is this ref thing? Now I want to quickly clear up a misconception. So in Hazel, the game engine series version of Hazel, this, which is a public GitHub repository, we do have inside base.h ref being defined as a shared pointer. So in this like free 2D game engine series version of Hazel, ref is in fact a shared pointer. However, inside real Hazel, so this is inside the big proper Hazel, ref is actually a class that we are going to take a look at in more detail over here in this video. I thought that it would make more sense to explain the concept of reference counting by taking a look at some examples. As we look at the examples, I'll explain more of it. We'll dive into the internals of how it works, and hopefully that will help some of you who have never encountered this sort of thing before. But fundamentally, reference counting solves the problem of I have an object that I eventually want to be destroyed, but I'm not quite sure when and how, and either way, I don't want to handle that. It's supposed to be a mechanism for automatic memory management. But I want to stress that sometimes this particular way of automatically managing your memory is your only option, because sometimes you don't really know exactly when or who will be last to use a particular memory allocation before it can be freed. So diving into this, what do I have here? I have a resource that I would like to be heap allocated and then used for some sort of lifetime. When everyone who is using this resource is done with it, I would like it to be deleted because no one's using it anymore. The idea is that this particular way of creating a resource is sort of replacing just a regular heap allocation. So if I did something like this or that, I would of course have to then at some point delete it. This just automates that. Why? Because this ref class will, inside the create function, actually create my new object on the heap, and then eventually, when the reference count hits 0, it will be deleted. So you can see that this new and delete is just being automatically done. It's abstracted away into this ref class. Now, there are many different ways that we can sort of automate or abstract new and delete. Of course, we could use a unique pointer. We could even use a shared pointer. In this case, we'll talk about the nuances of those specific other techniques, we'll call them, later in this video, but that is the gist of how this works. This isn't actually a compile error, by the way, this is just Visual Studio. Okay, so to explain the actual concept of reference counting, it works like this. It's simply a way to track how many different things are using your resource, with the idea being that once the reference count hits 0, nothing is using your resource, and therefore it can be freed. So to demonstrate this practically in this case, when we create this resource, exactly one thing is using it. This variable resource is holding our actual resource. That is our one reference to it. So therefore the reference count is 1. When we then want to print it, what are we doing here? We're grabbing this resource variable and we are passing it by value. We're copying it into this print ref count function. So therefore, at this point within this scope over here, the reference count of resource is 2. Then we print it. So we should see 2 in the console. And then when we hit this and we return back over here, this particular resource variable that was created by us copying our original resource variable into this function is now gone. It's dead. It's been destroyed. And so our reference count falls back down to 1. Then we hit the end of this scope, and this resource variable is now done. It's destroyed. And so the reference count of our actual resource that is held within this resource variable goes down to 0, at which point it gets destroyed. And so by the time we hit this print line function over here, our reference count is 0, but also the actual object has been destroyed. Now, what is resource? Resource is a very, very basic class that just simply says that it was constructed, destroyed, and for a more complicated example later in this video, we have this as well. You may also notice that this is actually deriving from a class called refCounted. More on that later. So if I do actually run this program, then you will see the result. So we construct the resource, which happens over here. We print the resource ref count, which it is 2, as I explained. Then after this function returns, the reference count goes back down to 1. We hit the end of the scope, the reference count goes down to 0. Our resource is destroyed. And then finally our program ends. If I just pull this out and paste it into here and here, then this becomes a little bit more clearer. We construct the resource, we have a reference count of 1, we put it into this function, it goes up to 2, it gets destroyed, goes back down to 1, and that's it. So ultimately, this ref object just simply holds the pointer. So we have a pointer of a particular type. This is our heap allocation. This is what the ref class holds. That's all it is. It's just holding a pointer and it's providing all of this functionality around that pointer. What about the actual reference count? Well, that is stored in the actual resource. So in the resource class itself, it derives from ref counted, and the reason for that is because this has the reference count. It's just a normal unsigned integer. It is atomic because multi-threading is a thing. However, ultimately it's just a uint 32t. You can see it starts at 0. We have increment and decrement ref count, and when the ref class is actually constructed with a valid non-null pointer, then we will increment the reference count, which simply calls increment reference count on the actual object. Now, how can we speak about memory management without even mentioning Rust, the language that fixes it all? Well, at least tries to make it better. Why don't you find out for yourself and just learn Rust with Let's Get Rusty, the sponsor of this video. Let's Get Rusty focuses specifically on Rust education and job-ready training made by a fellow YouTuber with a YouTube channel all about Rust. If you're used to a low-level language like C or C++, Rust builds on that and tries to improve it with modern tooling, which helps greatly with safety and things like threads. Multi-threading can be difficult, and the strong safety guarantees built into Rust can help improve safety. All of this is exactly why companies like Google, Microsoft, and Amazon are adopting Rust more and more in production. And developers really enjoy using it. It keeps topping Stack Overflow's most admired language year after year. Let's Get Rusty runs structured programs for individuals and teams, and over the years they've helped thousands of developers actually learn Rust, become productive using Rust, not just watch endless tutorials and forget everything a week later. And here's the good news, they're actually running a new cohort next month. Spots are limited. Now's a really great time to check it out. Go to letsgetrusty.com/start with Cherno. Link will be in the description below to find out more about their training. Huge thank you to Let's Get Rusty for sponsoring this video. Now, this ref counted thing is kind of critical because this is the biggest reason for how this differs from what C++ already provides you with. The biggest question I get surrounding this is why do I not just use a shared pointer? Because this could just be a shared pointer and then you would have std make shared and that's it. Isn't that the same thing? Well, kind of. It works the same way, but it's different in a few crucial ways. The biggest difference is that shared pointer is not intrusive reference counting. It stores the reference count not as part of the object, but elsewhere. Make shared combines the allocation of the actual object and the reference counting block into one allocation, but it's still not intrusive. There's nothing in C++ that exists at the moment that is actually intrusive reference counting. The closest thing that's kind of widely available is something called boost intrusive pointer, but we don't want to use boost. Now, there is actually something inside the standard library called enable shared from this. This is the closest thing to intrusive reference counting, but the reference count is still not actually in here. You can see it's just holding a weak pointer. It's just that it allows you to make a shared pointer out of yourself. So I have an example here that we'll look at in a minute, but basically what I'm talking about is this over here, where we can make a shared pointer of our particular resource from this, because otherwise that's not really possible. So if you had your shared pointer over here, but then I wanted to actually be inside the resource class and then make a shared pointer out of myself to then submit somewhere, for example. I'll show you an example from Hazel in a minute, which will make more sense. But if I had something like this where I wanted to submit myself, you know, to the renderer, and then obviously the renderer will have to use me, so I want it to be reference counted because I don't know when the renderer will finish with me. I can do this by doing shared from this if I subclass it. So this is the closest thing to intrusive reference counting like behavior that we have, but still the reference count is not really inside us, so it's a bit different and basically worse. Here's a more concrete example from Hazel. So if we are in render command buffer, which is a ref counted class, and we want to submit ourselves to the renderer because this needs to run on the render thread, then I can make a reference counted object out of myself. And since the reference count is part of this object, it's not like, oh, I don't know what my reference count is because it's external. No, it's here. I am the reference count. So therefore, of course, you can make this ref object out of me. I'll just increment the reference count and then pass it off, hand it off onto a different thread. And of course, we're in a different thread now. So we don't know, maybe the main thread will finish with this first, but then the thread's still holding on to it. So in that scenario, we literally don't know who's gonna finish with this because it's all like multi-threaded, race conditions, whatever else. Let's look at an example I prepared that is multi-threaded. So we have this multi-threaded example. Let me shut off the other one and then we'll take a look at this one. So same story, I have ref resource, but then what I'm doing is creating 4 workers. These are 4 worker threads. I'm going to create one resource and I'm going to give it to the worker threads. So each thread is getting its own copy of this ref, but it's still the same resource. There's only one resource. I've created it once, I'm just giving it to 4 different workers that need to do things with it. What the workers are actually doing with it is simulating some work that's happening. It's calling use on the actual resource, which is just simply printing which worker is currently using it. We have this per thread random number generator that will simulate some sort of work for up to 100 milliseconds. So it'll just sleep. And then it will finish. Back on the main thread, we will of course wait for all of these workers to actually complete before we try and end our program. And then this is in a scope because as soon as we unleash the workers, we're kind of done with this resource. We don't really need it on the main thread anymore. We're happy to not use it on the main thread, but the workers are still going to need it. And specifically, we don't really know which worker will finish last with the resource, do we? Because, well, in this case, we're simulating a random amount of work. So which worker will finish last? Let's have a look at how this program runs. So we construct the resource, worker 1, 2, 3, and 4, and 0, actually, had me going there. 1, 2, 3, and 0 have all begun. They're all using the resource, so they've called that use function. And then they're sleeping for a random amount of time. They're processing, let's just say, for a random amount of time. Worker 2 finishes first. Of course it would because it only took 5 milliseconds. Then 3, 1, and 0. Then the resource gets destroyed. So notice how worker 0 finished last in this case. Let's run it again. This time, worker 3 finished last, and then the resource was destroyed. So you're kind of seeing the picture here with the lifetime pretty clearly, I hope. We don't know the lifetime. We don't really know when exactly and who exactly should be responsible for this resource being destroyed. All we know is that when everyone is done with it, we want it to be destroyed. When it's no longer needed, we want it to be destroyed. That's the definition of memory management. When it's not needed, destroy it. And that is what reference counting does. That's what shared pointers do, because shared pointers are an implementation of reference counting. They're just not intrusive reference counting. And again, if you want intrusive reference counting, you have to use your own or use Boost, but let's not. Come on, let's not talk about that. And that is why Hazel has this ref class. Now, if we look at a shared pointer example of the same thing, it would look exactly as you would imagine. We would just be creating shared pointers instead of refs, and it's largely the same, but we can't do things like this without enabling shared from this. But then even so, it's still not intrusive reference counting. I hope you're getting the idea. If you guys enjoyed this video, please don't forget to hit the like button below. Let me know what you want to see next as far as C++ goes. This series is still alive and I'm still going to try and make videos when I have time. If you're interested in reference counting and you want to learn more about it, I highly recommend you try and implement it yourselves. This video should have given you enough information to try and implement it yourselves. I mean, the concept is really simple. When you create a copy of a ref, you increment the reference count. When a ref dies, you decrement the reference count. If it hits 0, delete the underlying object. That's it. Lots of nuances will creep up, but that's the basic idea, so give it a shot. From here, there are other things that exist within Hazel, such as weak pointers, weak references, because you may want to use this like a weak pointer from a shared pointer. If you want to see a video about how that works, let me know in the comment section below. Thank you guys for watching. I will see you next time. Goodbye.